All right, guys, Mr. Antonucci here, and in this section, we're going to talk about area, and we're going to do two main things: approximate an area and find the area under the graph of a function. Now, the area problem asks, given a function f defined and non-negative on a closed interval a to b, what is the area, we'll call it capital A, of the region bounded by the graph of f, the x-axis in the vertical lines x equals a and x equals b. So if we look at figure one here, okay, you have this region A bounded on the top by the blue graph of the function f, the x-axis and the horizontal line or vertical lines x equals a, x equals b. Now, to answer this question, how do we find the area of this region? We can approximate it by superimposing areas of a finite number of rectangles, as we see here in the second figure. Now, notice some of these rectangles stick out over, some of them stick out under. This one right here towards the middle, some of it sticks out, some of it's underneath. And so you're going to approximate the area. Why we use rectangles is because if you use rectangles, well, we look at figure three, the area of a rectangle is very easy. It's just the height of the function times the width of the interval. So um, we can easily get the areas of these rectangles here by using that formula. Now, if you have horizontal line segments, as in figure four, then you could just add those areas up to get the area um, for these three regions here. And it's a similar concept here. And you might have already kind of thought that if you make the rectangles thinner, you'll need more rectangles, but they'll better approximate the area under the curve. So that's kind of the concept that we're going to use here with this type of problem. So we want to approximate an area of the region bounded by the graph of y equals 1 half x plus 3, the x-axis and the lines x equals 2 and x equals 4. So we're first going to draw this region right here. So here's x equals 2, x equals 4, and then the region would be this region right here. So it looks like a trapezoid, which we know how to get the area of that. But let's first start by drawing a rectangle of height when x equals 2. So we'll go right here. The height of the rectangle is 2, and the width of the whole region, if we go across the whole thing, is 2 units wide. Okay, so 4 times 2 equals 8. Now we missed this part of the area under the graph, so we know that that's going to be less than the true area. We'll call it A. Okay, so let me get rid of this. Now, if we have the same region, but we use the x value when x is 4 to get the height of the rectangle, then the height of the rectangle there is 1 half 4 plus 3 is going to be 5. So that height is 5. And then if I finish the rectangle using that height, I get 5 times the width of the interval, which is 2 units. And that gives me 10. That's going to be greater than the area, the exact area. So I know now that the area has got to be between 8 and 10. But also, I could use more rectangles. So I can, if we use, let's say, 2 rectangles. So let's get this here, like this. And we could try to get the area using 2 rectangles. But before we do that, we could actually improve our guess at the area by dividing this into 2 subintervals like we said. So now if we draw 2 rectangles right here, okay, and then use the left or the beginning part of each interval. So right here in this rectangle, and then when x is 3, this rectangle. So the area is going to be f of 2 times 1 plus f of 3 times 1. Notice the width of the interval is only 1 unit now. F of 2 is going to be 4 times 1 plus f of 3 is going to be 4.5 times 1. And then you would get 9.5 or 19 over 2. Okay, so now I know that the area is greater than 9.5, but if I used the right endpoints here with these two, so this one like this, and then this one like that, then the area for that would be f of 3 times 1 plus f of 4 times 1. We already said that f of 3 is 4.5 times 1 would be 4.5, and f of 4 is 5. So now we get, I'm sorry, that was 8.5, which would be 17 over 2. This is 8.5. This is going to be 9.5, which is 19 over 2. So the areas now we know is between 9.5 and 8.5. So now we have a better approximation of the area under this graph. And we can keep doing this. As the number n, we'll call it, of subintervals increases, the approximation of the area improves. And notice also that the area for one rectangle has an error in approximating the true area by 1 square unit, but for n equals 2, the error would end up only being 0.5 square units. Now we can actually get the true area here because we could just make it a trapezoid and go from there. Okay, so in general, the procedure for approximating area is based on the idea of summing the areas of rectangles. So we're going to talk about the area A of a region bounded by the graph of f of x, where f of x is non-negative, the x-axis in the vertical lines x equals a and b, as the area under the graph of f from A to B. Now we make two assumptions or qualifications. F has got to be continuous on that interval, and f is non-negative on that interval. Now we're going to divide that interval into n non-overlapping intervals. So if we go from, A to B, we're going to divide it up into intervals. So this would be like x1, x2, and all the way up to xn. The first subinterval would go from A to x1. The next interval would go from x1 to x2, and so forth. And then the last one would be xn to b. Okay. And if they each have the same width, we'll call that delta x. And delta x is actually going to be the width of the interval divided by how many subintervals you do. So the width of the entire interval is b minus a. You divide that by the number of subintervals or the number of rectangles, and you would get delta x. So since f is going to be continuous on that interval, by the extreme value theorem, there's a number in each interval where f attains an absolute min, and another one where f attains an absolute max. So we can essentially talk about the area of each rectangle. The first rectangle, if you use the upper side, so like the first rectangle is going to go from A to x1. So that would be f of x1 times delta x. That's going to be the area of that first rectangle. The next rectangle would be f of x2 delta x plus so forth and so on. In general, if I let Cn be the right endpoint of whatever rectangle we're on, the area of the nth rectangle is going to be f of Cn times delta x. Okay, so we're developing a formula here um, for the area. Now, the sum, so that's the area of one rectangle, but I have multiple rectangles that we're going to add up here. So the area is approximately equal to f of C1 delta x plus f of C2 delta x plus dot 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 f of Cn, however many rectangles you are, delta x. And we can actually write this in shorthand notation using the summation notation. So I equals 1 to n of f of Ci delta x. Now, all that means is add up all of the function heights times the width, and you'll get the approximate area. Notice I used wavy equal signs here. Okay, so we want to approximate area using lower sums. So approximate the area A under the graph of x squared from 0 to 10 using lower sums. We'll call that lowercase s sub n for 2, 5, and 10 subintervals. So the actual region goes from 0 to 10. Okay. Now for part A, if n equals 2, we're going to divide it into two subintervals. So our delta x is going to be 10 minus 0, because we go from 0 to 10, divided by 2, which is 5. So every 5 units, we're going to make a rectangle. Okay, so the first interval goes from 0 to 5, and then the next subinterval goes from 5 to 10. So we need to um, go ahead and begin calculating this. So this is going to be the sum, I equals 1 to n, or 1 to 2, actually, of f of Ci delta x, which would be f of 0 times 5 plus f of 5 times 5. Now, f of 0, remember we're using x squared, is just 0. So this ends up being 0. And that f of 5 is 25. So 25 times 5. And then we end up with 125. So basically, graphically, what we did was we did this first rectangle was we used the left endpoint of that subinterval, so it had no height. The next rectangle is right here, and we can see that under approximates it. So I know that this is less than the true area. Now B, if I do it with 5 subintervals, okay, some things are going to change. I would have 10 minus 0 over 5, which gives me 2. So now I'm going to partition this into 5 intervals, each being 2 units wide. So the area is approximately the sum, I equals 1 to 5 of f of Ci delta x, which is going to be, I could factor out the delta x, which in this case is 2. So I could do 2 times f of 0 plus f of 2 plus f of 4 plus f of 6 plus f of 8, and that will give me my 5 subintervals. Okay, so it's going to be 2 times 0 plus 4 plus 16 plus 36 plus 64, which equals 240. Now, if I go every 2 units on here, okay, so we 2, 4, 6, 8, and I make the rectangles using those left endpoints, you can see that it's still an under approximation, but I've covered more of the area under the graph. Then for part C, we want to do 10 subintervals. So delta x equals 10 minus 0 over 10, which is 1. So I'm going to have 10 subintervals, each 1 unit wide. So the area is going to be approximately the sum I equals 1 to 10 of f of Ci delta x. So it's going to be 1 times f of 0 plus f of 1 plus f of 2 plus all the way up to f of 9. Don't do f of 10 because when you get to 9, that would be the left endpoint of your last and 10th subinterval. Okay. Now, this is going to add up to eventually 285. And again, it's still an under approximation, but I'm getting closer and closer and closer to the true area under the graph. So in general, the error due to using these sums is going to decrease as the number of subintervals increases. So this brings us to the definition of area under the graph of a function from A to B. So suppose a function f is non-negative and continuous on a closed interval. You partition that interval into n subintervals. Each has a width of delta x, which you compute by b minus a over n. And then the area under the graph is essentially the limit as n approaches infinity for that um, for that sum of individual rectangles. Okay, so that's it for this one. Please reach out if you have any questions. Take care.